concepts in a very thorough way, and also we are going to solve numericals from various competitive examinations as we go forward. We are starting with the basic chapter, that is units and dimensions. People think that in units and dimensions questions comes from some basic chapters. We don't some basic or predominantly from dimension analysis. We don't need to take this chapter very seriously and so on like that. The reason is too many basics are actually embedded within this respective chapter itself, and as if you don't understand the basics thoroughly, okay, and yeah, I can see the video has been streamed here. Yeah, so now I can see it's proper here. So what I'm saying was, like, though this chapter is small, we should not overlook upon this, because too many basics, majorly whenever you solve a numerical, what are the correct units you should solve, how actually we should uh, put the units, how we should convert the question or convert the numbers, everything is actually there in this chapter. So if you're clear about the basics whichever are there in this respective chapter, then we can definitely, if all the basics are clear in this respective chapter, then you will feel very easy in the coming chapters. Fine, so let's go ahead. You guys can continue putting doubts or anything in the chat here, and I hope there is no problem with the streaming here. So I can see the video is coming up. So before starting the chapter, I would like to introduce myself. So myself, UJ Prasanna Kumar. I have around 10 years of teaching experience, and in all these 10 years I taught for various competitive examinations, which includes GATE, SSCJE, ESET examination, Combined Defense Service examination, and various examinations. So we will be understanding thoroughly in this respective live lectures, and you're gonna see that, like, you'll be able to solve any question no matter whatever is your pace of learning. So please listen carefully, and just you need to follow whatever I'm saying. So instead of getting distracted here and there, you just listen carefully here. And if you're really liking the video, and if you're really getting benefited as we go forward into the slides, I request you all to please don't hesitate in subscribing and clicking on the bell icon. So what happens is, as we did not set the schedule of the classes yet here, we will be releasing the schedule pretty soon. So what you need to do is, you need to actually click on the subscribe button and click on the bell icon, so that you can understand when the class is actually being streamed. So you'll not be missing out any class, and if you're missing out any class in between, I request you to go to the video later and come to the class here. Otherwise you'll be missing out some basics. Fine, so let's start with the concept of physics here, the subject of physics here, and where actually units and dimensions come. So units and dimensions actually came by the way we are understanding physics, or by the way we are applying physics. So physics means what? Basically is, generally in our olden days, people had the habit of observing nature. So whatever happens in nature, according to that they started believing, or they started behaving accordingly. So for example, if you have climate, so in the months of May and June we have summer, in the months of August, September we have rains, in the months of December, November, etc. we have winter season, and so on like that. So what people started doing was, in the time of rains they started putting seeds, starting agriculture, and in the time of summer they started reaping the harvest. So people started inculcating the habit of observing the nature and going according to that one. So by observing the nature, these laws of physics actually came. So we hear about a lot regarding Newton's first law of motion, Newton's second law of motion, gravitational constant, all those things. Everything came primarily from observing the nature. Understood here? So when they started observing the nature and they started writing concepts related to physics, so too many things have come up. So if you open any physics textbook, you hear about these words: mass, length, time, force, temperature. Not only these, elastic constants, rigidity modulus, electric current, all those things. So whatever terms you generally see in any physics textbook are nothing but physical quantities. So as you know, guys know that we are preparing for competitive examinations, and in these competitive examinations you will not be experiencing too many tough questions, and you should be inculcating the speed of solving more number of numericals. So what we are going to do is we'll cover up the concepts very fastly without wasting our time in one of the class, and in the subsequent class we will take up numericals continuously. So I request you all to understand the concepts very thoroughly, and please don't miss out concepts, because questions, if you're listening to the concepts or learning concepts when you're solving the numericals, then that's not the correct way. You'll always have a doubt. So you should have a clarity about the concept first, and then you should solve numericals. So that's what we are going to do here. So I can see that like 2 people are live here. So I really appreciate for joining the live here, and I can understand that you guys are very serious about your career. So I will make sure that you are going to understand these concepts in a very thorough way. Fine, everyone. So physical quantities means what? So in textbooks there are too many definitions and 2-3 lines of statements and all. What you need to understand is, you don't need to mug up the definition of physical quantity. Just remember that whatever terms you hear in physics, all are physical quantities. And primary definition that is given is, the quantity that can be measured directly or indirectly is nothing but a physical quantity. So examples of physical quantities are mass, length, time, force, temperature, electric current, momentum, many things here. Fine. So these physical quantities should be quantified, right? So to quantify them, ante, that means you need to give some measure for them. Like for example, you have mass and you want to take some rice or something, so you want to quantify it, right? How many kgs of rice is there, how many grams of rice is there? Or if you take water, how many liters of water is there? If you take some distance from Hyderabad to Delhi, what is the distance? So it should be quantified. So the physical quantities need to be quantified. The physical quantities need to be quantified. You're understanding you're understanding properly here. So they should have some units to be given here. For example, if you take olden days, nowadays we have these standardized units like kgs, meters, kilograms, seconds, Newton, kelvins, centigrade, Fahrenheit, etc., and so on, like that. In the olden days, you'll see, before Britishers came up, so you never ever had, or if you see the stories of Mahabharata or even olden medieval history or ancient history of India, you might not have encountered the words like kgs, etc., right? So those things came up after this globalization, which actually happened or primarily started with the coming of British people and other foreign people into our country here. So whatever the units which are used worldwide outside, they started penetrating into our country as well. That's the reason why today we have kgs, seconds, all those things, right? So earlier it was not there. If you go and ask your grandmother, they'll be having different types of units. So based on the place in which they're actually staying, they'll be having their own way of using units there, right? Understand? So the standardized units generally which are used are, like for mass, that is kg, for length it is meters, for time it is seconds, for force it is basically newtons, temperature it is centigrade, and so on, like that. So we'll discuss regarding them very detailed way here. So only thing which you have to understand now is, physics came up by observing the nature. To understand and observe the nature, we need to have, or we need to define some physical quantities. So these are all the physical quantities here. Now to define physical quantities, we require units. So units are like kg, centigrade, kilograms, meters, and so on, like that. So these units are different across different countries. Till today, if you remember, though in India and many countries, distance between cities is measured in kilograms or written in kilograms, in America it is still in miles. Am I right? So still they use different units, miles, although there is a conversion formula between miles and kilometers there, but throughout the globe we are not using same units. Similarly for mass we are using kgs, etc. But if you go to England, you'll see that they are using pounds. So still the uniformity of the units is not there. Clear? So but some of the units are actually standardized, and those are given some standard definition so that it is followed the same throughout the globe. So if you see meter, so meter is defined by length of the distance, that means how much length a light has traveled in vacuum for 1 by this particular big number, 3 to 10 power of 8 approximately of a second. That means in 1 by, like you can understand 1 by 10th of a second, 1 by 100th of a second, 1 by thousandths of a second, and so on like that, right? So 1 second you can understand how small it is. So whatever is the distance the light can travel within 1 by 3 into 10 power 8. 3 into 10 power 8 means if it is 3 into 10 power of 5, it is 3 lakhs basically. 10 power of 8 means 3000 lakhs. 1 by 3000 lakhs means 1 by 3000 lakhs means 30 crore. 1 by 30 crore time, okay, or 30th 1 by 30 crore part of second is a time. Okay, within that particular time, whatever the distance is traveled by light in vacuum. So the medium is also very important when you talk about distance, when you talk about light here, because light travels at a different speed and different mediums. So we are taking vacuum. So vacuum means there's nothing between those or within that volume there. So whatever the distance the light is traveling over 1 by 30 croreth of a second is given by meter. Similarly for kilogram also some standard is there. So in Paris there is a organization, International Bureau of Weights and Measures. Just like you have museums, you have some big buildings, parliament, etc. in various cities there. So in that particular building there is a cylinder which is made up of platinum iridium. So that is having mass of 1 kilogram. So 1 kilogram is defined with respect to that across the globe, and similarly for second as well. So a cesium atom will be vibrating some number of times in a atomic clock. So whatever the time taken for vibrating these many number of times, you can see this big number which is looking like a phone number. So that particular time is given as second. Similarly for Kelvin is given as 1 by 273.15 time of a triple point of water. So that's the thing here. So you don't need to remember all of them. Just if you are able to remember the first three, meter, kilogram, second, that is enough, because we can expect a question from those first three terms here in any of the competitive examinations whichever we are targeting. Fine guys here, but understand the logic. These units came because everybody in the globe should understand same thing by kilogram. If you say kilogram in Hyderabad, if you say kilogram in Vijayawada, if you say kilogram in Delhi, everywhere the person, the shopkeeper should understand the same. That's the requirement here. Understood guys here? So that's the reason why these units are actually standardized: meters, kilograms, second, and so on like that. Fine. So we understood what is a physical quantity. These are the terms whichever you hear across physics. These physical quantities requires units. And why do we require units? Because these units should have uniformity across the globe here. That's why they are actually defined here. And these physical quantities are actually classified because some physical quantities are fundamental physical quantities, some are derived physical quantities. You don't need to mug up anything. Just look at this slide, you'll understand from this. If you see slide number 9, length, mass, time, temperature, electric current, luminous current, amount of substance, all these terms are given as, or given the name or into the category as fundamental physical quantities. And if you see these terms, force, area, volume, velocity, acceleration, energy, all these are given the name as derived physical quantities. Can you understand the difference between the both? So if you see, every derived physical quantity can be written as a combination of fundamental physical quantities. So if you see force, you guys know force formula is mass into acceleration, right? So mass is a fundamental physical quantity, and you take acceleration. Acceleration is nothing but velocity per time square, basically rate of change of velocity per time, rate of change of velocity basically. Again, velocity can be written as distance per time, so distance by time square. So distance, which is length, basically is a fundamental physical quantity, and time is actually another physical quantity here, fundamental physical quantity. So you can see that all these derived physical quantities, I'll write down regarding each and every derived physical quantity in a more clear way little later. Let's understand that these fundamental physical quantity, the derived physical quantities can be written as a combination of these fundamental physical quantities, right? So just remember that these are all these fundamental physical quantities, and you cannot write down or break them into any big formula. Length means length itself, mass means mass itself. Like for example, if you take force, force is mass into acceleration, so it can be broken down into fundamental physical quantities. Area can be taken as length into breadth. So length is one fundamental physical quantity, breadth is also another type of length, which is another fundamental physical quantity. So you can see that the area can also be derived or broken into fundamental physical quantity, and so on like that. But it is not possible to do the same for these fundamental physical quantities. Length cannot be broken, mass cannot be broken, time cannot be broken or written in terms of any other formula, and so on like that. Fine. Let me show you how to break these or write these derived physical quantities in terms of fundamental physical quantities. So if you take force, force F is nothing but mass into acceleration. This acceleration is nothing but velocity by time, and this velocity is nothing but distance by time. So you'll get it as m v by t, which is m l by t square. Mass, so m is mass, l is length here, and you can see t is time. So we derived this force into fundamental physical quantities here. Similarly, you can take area. Area formula, if you take it, for a rectangle it can be written as length into breadth. For a circle it can be written as pi into radius square. So you take any shape basically. If you take surface area of a sphere, so that can be written as 4 pi radius square. So whatever you take basically, so this is a fundamental physical quantity, this is a fundamental physical quantity, this is a fundamental physical quantity, this is also a fundamental physical quantity, and so on like that. So you can see that here this area can be broken down into a fundamental physical quantities here. So that's the reason why area is also one of the type of derived physical quantity. Similarly, volume. So I'm simply taking a cuboid here. So volume can be taken as length into breadth into height. All of them are fundamental physical quantities. Understood? Clear? Similarly, you take velocity. So velocity we have written already is distance by time. Velocity is distance by time, so that can be divided. Acceleration, velocity by time. Again, velocity is distance by time. Like that. You can write down for energy as well. Energy is equal to work done, force into displacement. So force again can be broken down into fundamental physical quantities. Clear guys here? So like that you can easily classify fundamental physical quantities and derived physical quantities. Fine guys? Two of the terms are there which are given into the category of supplementary physical quantities. They are not into this bunch of fundamental physical quantities, or they are not into the bunch of derived physical quantities. Fine? Clear? So in supplementary physical quantities there are two terms and their respective angles are also given here. Plane angle, so whatever you write down on a plane, like you say that there is this x-axis and there is this line and this is this angle alpha, this is this angle alpha here. So you're showing everything on a plane here. So this alpha is equal to 30 degrees or 30 by pi radians. Fine, sorry, 30 by 180 basically, because 180 degrees is equal to pi radian, 180 degrees is equal to pi radians, and 30 degrees is nothing but 30 into pi by 180. This is the radians here. So units basically, just remember this one. Okay, so it's a plane angle basically. So that is written either in radians or that's either written in degrees here. Fine, radians or degrees basically. Clear? Fine. And you take solid angle. So solid angle means basically three-dimensional angle. For example, you take a floodlight here. So floodlight will be having a conical shape. So it will be in a conical shape here. So whatever you are taking here, this particular angle in this three-dimensional form is measured or given the name as solid angle, and its units are steradian. So if any question comes in any of the examinations that what are the units for plane angle, what are the units for solid angle, you can easily answer them now. Let's go forward. Whatever units you take, they should be universally or internationally accepted. They should not change from time and place. They should not change with temperature, and so on like that. You don't need to mug up them, but understand the logic basically. Simple example I'm giving you. You take 1 kilogram, like I said, 1 kilogram in Hyderabad, 1 kilogram in Hyderabad, Vijayawada, or 1 kilogram in Delhi, everywhere, or 1 kilogram in London, or 1 kilogram in New York, everywhere it should be same. Everywhere it should be same. Understand? If it is changing, then we cannot use that as a unit, right? For example, someone says 1 feet, measure with your legs. So someone's feet can be longer, children's feet can be shorter. So that is not standardized there. So today 1 foot or feet are standardized basically. So that is not a big problem now. But if it is not standardized, nowadays we have a complete strong formula, a standard formula between feet and meters, right? So if that uniformity is not there, means we cannot call it as a unit. So that's a basic requirement here. And also it should not change to temperature or anything as well. So all these things should be satisfied. Okay, so now let's look into types of units here. So I don't see any comments or any doubts in the chat here. So I hope there is no confusion. Clear, everybody? So if any doubt is there, anything you would like to ask me, you can immediately ask me in this live chat. The reason why we are conducting live class, the reason is to clear doubts live, to clear doubts on the spot. Okay, fine. So types of units basically. So here these units, nothing is wrong, nothing is right. These are just the units which were used in different parts of the globe over the time. That means, like I was saying, today also in England people use pounds for measurement of mass instead of kgs, etc. In America, for length or basically distance between the cities, they use miles, like that. So based on different types of units which are used across the globe, these systems are named here. We will not be using any of these three systems. We will be using a standardized one which was started or which was established in 1971. So there is CGS system where length is measured in centimeter, mass is measured in gram, and time is measured in second. FPS system where length is measured in foot, mass is measured in pounds, and time is measured in seconds. Similarly, MKA system, length is measured in meters, mass is measured in kilogram, and time is measured in second. Understood, guys? Here, fine. So like this, everybody is using different system of units. So in 1971, a conference has happened between scientists and many people, and they decided that let's go with some standardized units basically, and they gave the name as SI units, basically International System of Units. That means instead of going with centimeter, foot, etc., let's all go with meters. Instead of going with grams, pounds, kilograms, etc., differently, let's go with kilogram uniformly. For time, let's go with seconds, and so on like that. So that's what we call SI units there. So what we should learn as far as our competitive examination is concerned is, we have to make sure we convert everything to SI units. We have to make sure to convert everything to SI units when you are doing the calculations. Fine. So in SI units, you can see the units for various physical quantities here. For length, it is meter. For mass, it is kilogram. For time, it is second. For temperature, it is Kelvin. For electric current, is ampere. For luminous intensity, it is candela. For amount of substance, it is mole. Fine. And similarly, if you go for derived physical quantities, obviously you can understand from the actual formula for them. So for area, it will come out to be meter square. For volume, it comes out to be meter cube. For velocity, it comes out to meters per second. For acceleration, it comes out to meters per second square. For force, it comes out to newtons. Clear, everybody? Like if you go with angle, it is actually taken in radians basically. Fine. So you hear about these terms newtons, joules, watts, etc. from these SI units only. That's the biggest advantage here, and it actually includes many system of units. So I hope whatever the concept I'm explaining you here, you're able to understand very thoroughly, because in the tomorrow's class or the next class whenever we take, we will be conducting, or straightforwardly we'll be going with numericals directly. We'll not be waiting. Understood? So we will be getting numericals, and we'll all be able to solve very thoroughly without any problem. Understood? Clear, everybody? Please listen carefully here. And also remember about these multiples and submultiples here, because you already heard about tens, hundreds, thousands, and so on like that. But we need to remember about others as well, because sometimes it is multiplied by 10 power 6. 10 power 6 is given the name as mega. 10 power 9 is given the name as giga. 10 power 12 is given the name as tera, and so on. So sometimes we can expect a question from these names as well. So I request you all to take screenshots or take the notes and feel or prepare them well, so that you will feel easy when we are solving numericals. Fine, guys? Similarly, going below, that means here we multiplied by 10. I mean, we are going on multiplying 1 with 10, hundreds, thousands, and so on like that. Here we are dividing by 10, hundreds, thousands, and so on like that. So here we see that these are deci, centi, milli, micro, nano, pico, and so on like that. So mostly in these, remember for mega and giga, and here remember for micro and macro, because milli, centi is already known to you. Fine, guys? I believe it is completely clear. Now we are entering into the most important concept in this chapter, and we are wrapping up this respective concepts for this chapter here. So after that, we'll be continuously going with numericals in the next class. Okay, it is dimensional formula. Why we have to study dimensional formula, what actually happens, what is use of it, everything will come to know about this later. Just understand for now. Okay, if you take length, breadth, radius, thickness, though according to English they are different, but according to physics they are same. They are basically length, right? Similarly, seconds, minutes, hours, days, according to English they are different, but according to physics they are simply nothing but time, right? We can convert the units from one form to other form, but they are nothing but time itself. So dimensional formula, if you want to write down, first of all we need to know about the dimensional formula for these common words. So again we take those common words of fundamental physical quantities and derived physical quantities. So for fundamental physical quantities we already know that we cannot go beyond separating them. We cannot go beyond separating them, right? We can't go beyond separating them. So if you take length, mass, time and so on like that, they are given like this. Length is given dimensional formula as L, mass is given dimensional formula as M, time is given dimensional formula as T, electric current is given the dimensional formula as I, temperature is given the dimensional formula as K or theta, luminous intensity is given the dimensional formula as C, it's basically candela, units are candela and the symbol for dimensional formula is given as C, and amount of substance is given as mole. Okay, clear? So using these you can easily write dimensional formula for derived physical quantities. So if you guys don't have any doubt till now, then I will explain how to write down dimensional formula for each and every term now, and we can expect a question from these directly. So though we may not be having a question directly now on the screen, these are all the concepts which can be expected to come in terms of numericals. So we should be ready for that one. Fine everybody? Okay, so let's be ready here. So area, if you take it, so I'm writing down dimensional formula for each and every derived physical quantities here. So first one is area. So like I told you, area, if you take it, that can be taken as length into breadth. Various shapes have different areas, right? Different formulas. That can be taken as pi r square. Surface area of a sphere can be taken as 4 pi r square, right? So if you take surface area of a cylinder, that is 2 pi r into L. Okay, so area can be of any form. So area of circle, so whatever you take, you see that length and length square is the fundamental physical quantity here. So fundamental physical quantity, dimensional formula here. So for area we will get the dimensional formula as simply L square. So it might look very easy when you write down for area, but when you write down for acceleration in the examination you can get confused. So we should not be feeling overconfident when I'm explaining some easy concepts here, right? So let's go one by one. Volume. So if you take volume, if you take for a rectangle or a cuboid, basically this is length into breadth into height. If you take for a sphere, volume is 4 by 3 pi r cube. So like that, if you take for any shape volume, for a cylinder, if you take it for a cylinder, so here it is cuboid, so here it is sphere. So for a cylinder it is pi r square L. So you're gonna observe that L cube, basically L square into L cube is basically the dimensional formula for this volume. Fine. Similarly, let's take velocity. velocity or speed, if you take it, velocity or speed is nothing but we'll discuss regarding difference between velocity and speed later. For now, at this level, let's understand it is simply distance per time. So distance has dimensional formula as L, time has dimensional formula as T. So this gives it as L t power minus 1. Velocity or speed is L t power of minus 1. So now we take force. Force formula we have it as mass into acceleration, right? And this acceleration is nothing but velocity per time, and this velocity is again distance per time. So this gives as mass m. So time is a fundamental physical quantity, right? So its dimensional formula is already known to us. So it is t. So there is velocity here, and velocity is distance per time, so it is L by t. Let me substitute there. So we have it as m L t power minus 2. So force is m L t power of minus 2. Fine. Let's go with density. So density, if you take it, density is basically what is the mass per unit volume. So mass is already a fundamental physical quantity, and we already have this dimensional formula as m, and volume we already got the dimensional equation as L cube here. So this gives us as ml power of minus 3. Let's go with angle. So how can we get dimensional formula for angle? We'll take one formula for angle here. The basic formula is, if you have an arc like this, and this arc is part of a circle, so this is the radius r. So this arc length is given by r theta if this angle is theta here. So arc length, which is length here, L is equal to r theta. So angle theta is given by the formula L by r. So this is arc length by radius of the curve. So arc length dimensional formula is L, radius dimensional formula is also L. So this is 1. Hence theta is dimensionless. Basically theta is simply dimensionless. Okay, fine. Similarly, let's go with the next one here. Acceleration, which we have already discussed. I'll write down again so that you can write down your notes. So the acceleration comes out to be L t power of minus 2. Fine. Okay. So let's go with the remaining ones here. Linear momentum. So linear momentum means basically mass into velocity. So we know for mass the dimensional formula is m, and for velocity this is nothing but L t power of minus 1. We already discussed earlier, so you can understand from that one for velocity. Next one, weight. So weight is nothing but force. Force is nothing but mass into acceleration. So you have mass, acceleration is L t power of minus 2. So we got the physical equation like this. Then we have this next one, torque. So if you don't know about this formulae, don't worry, because you'll be learning them in the coming chapters. So for example, if you want to know the formula for torque, so torque formula is force into distance. Force distance is ml t power of minus 2. Distance formula is L. So this comes out to be ml square t power of minus 2. 11. Pressure. I hope you guys know what is pressure. Pressure is nothing but force by area. So force fundamental physical quantity is m, L t power of minus 2 and L square. This comes out to be m L power minus 1 t power minus 2. Right? Similarly, let's go with kinetic energy. So it is nothing but half mv square. So when you take a constant, you should understand the dimensional formula for any constant is 1, or whenever you say dimensionless, you should put it as 1. So mass m here and a velocity is nothing but distance per time, so L t power of minus 1. So it is m L t power minus 1. That is the formula here. Done. Again, potential energy. We know formula for potential energy is mgh, where g is acceleration due to gravity. G is nothing but acceleration due to gravity, right? So acceleration dimensional formula we already know. So you can write down like this: m, acceleration is distance per time square, L t power of minus 2 and L. So it comes out to be m L square t power minus 2. So what you need to understand is whether it is potential energy or whether it is kinetic energy. Just a minute, there is a mistake here. M L t power of minus 2 into L, half m v square. Sorry, it is v square, right? Yeah. So you can see that no matter whether it is potential energy or kinetic energy, you have same units here. You have same units here, or same, just like they have same units, they have same dimensional formula. So you have to keep in mind that when the quantity is same, just the type of the quantity is different. That means energy, kinetic energy, potential energy, electrical energy, light energy, sound energy, everything will have same dimensional formula. Okay, so you can write down a small note point here to understand or remember in a more easy way here. As far as units are same or quantity is same, the dimensional formula will remain same. The dimensional formula will remain same. Okay, clear? So I'm just writing down the example so that when you refer your notes, you'll be having complete clarity. You take potential energy. So you take kinetic energy. You take light energy. You take sound energy. Right? So all of them, they'll have same units basically, right? Joules, etc. So all will have dimensional formula as ml square t power of minus 2. Ml square t power of minus 2. So you don't need to know the formula for sound energy. You don't need to know the formula for light energy. We can simply say, as far as we are concerned, it is simply energy. So simply the formula, dimensional formula, will be ml square t power of minus 2 itself. Fine guys, let's go with the next one, and we are going towards the end of the today's class. Power. So power is nothing but energy per time. Okay, power is nothing but energy per time here. Energy per time. So energy has the dimensional formula which we have already discussed here. Again, ml square t power of minus 2, and there is time. This comes out to be m L square t power of minus 3. Fine guys, so this is the dimensional formula for power. Clear everybody? I hope there is no confusion at all. So let's discuss about these last two slides, 25 and 26, and that completes our concepts for today's class here. Stress and strain. So stress basically is force per area. So already we discussed for pressure, force per area. So ml power of minus 1 t power of minus 2. Done. Strain, that is change in length by original length. So this is length by length, that means 1, that means dimensionless. Fine, clear? Let's go with the last one and stop this today's class here. Principle of homogeneity. And this theorem is going to be very useful across our concepts, all the concepts. Okay, in many of the numerical they can expect you to use this theorem basically, or the principle. This says that whenever you have any equation you take it, F is equal to ma, momentum equation, mv, anything, any equation you take it. For example, you take mathematical equation that a plus b whole square is equal to a square plus 2ab plus b square. Any equation you take it, this theorem says that whatever units are there on the left hand side, same units should be there on the right hand side as well. Otherwise that equation is wrong. That's a very, very simple thing you have to keep in mind here. Okay guys, so that is the definition of this principle of homogeneity as far as this units and dimensions is concerned. So we have completed the concepts which are related to units and dimensions for all our competitive examinations. In the next class we will back to back solve the numericals across all the competitive examinations, and whatever small concepts whichever are not discussed we will be discussing at the time of that numerical itself. Fine guys, so thank you so much everybody. It's a very good experience to interact with you all. So in the next class I'm expecting that you guys will be referring to your friends, and we will be achieving good number of strength in the class, and we'll be solving good number of numericals, and we will be targeting to get the best ranks across all the competitive examinations whichever you are trying. Thank you so much everybody, all the best. This is your Prasanna Kumar signing off. We'll be meeting in the next class. We'll be getting to know about the next class schedule pretty soon, so please click on the subscription button and also bell icon so that you'll be notified regarding the upcoming class. Thank you so much everybody, all the best.